Hi guys, Becky the Science Tutor here, and today we're going to dive into one of my favourite topics, the Group 1 alkali metals. This was an absolute firm favourite that I used to love to do in the classroom. Okay, so last session we looked at the periodic table and we looked at the work that had been done, particularly by Mendeleev, to arrange the elements not only in order of their atomic weight, but in order of their chemical properties. And in his table, we saw that Group 1 was starting to form. So within Group 1, we have lithium, sodium, potassium, rubidium, cesium, and francium. Okay, now when we spoke about Mendeleev's table, we explained that the reason that elements have similar chemical properties is down to their electron structure. So in Group 1, they are all familiar, they're all similar because they all have one electron in their outside shell. Okay. Now, again, as we spoke about electron structure and we were talking about that development of the table last week, I said to you can gain so much information just by looking at the position of an element within the periodic table. So we're going to learn, and we know that Group 1 are quite reactive metals, and this is because of that one electron in the outer shell. It ideally would like to get rid of that electron. Group 1 are metals. Metals always lose their electrons, so it's looking for somewhere to donate that electron to. Now, in terms of being metals, Group 1 are a little bit unusual in the fact that they are quite reactive. If we think about the transition metals, the section in the middle, that I would call more typical metals, that I think of like door handles, chair and table legs, grates on the road, they're not reactive. We don't want them to be reactive. We don't want it to rain and suddenly the grates on the road start reacting. We want them to be unreactive. We want them to not to do very much, to just stay and be what they are. Whereas Group 1, we'll see in a moment, are really quite reactive. They react very readily with air. They react very readily with water. Okay, so we're going to see some different properties to them. Again, in comparison to those transition metals, they've got a low melting and boiling point, which makes them quite soft metals. Yeah, so we're going to see that we can cut them with a knife. It's quite tough, but we can still cut them with a knife, whereas your other metals are much more harder. So they have a low melting and boiling point. They're actually quite low in their density, and we'll see that when we watch a short video clip, because when we put them into water they float on water, showing that they've got that quite low density. Okay, so what we need to be able to do is to recognise patterns within groups. Remember, our groups are our columns, so in particular we're going to focus on their reactivity. Now, whenever we talk about a group and the patterns, we're always kind of referring to down the group. So we're going to have a look at how that reactivity changes as we move down the group. So we're going to focus on lithium, sodium, potassium, and look at their reactions and decide, do they become more or less reactive as we go down the group. Then we're going to explain that reactivity, linking that to their electron structure. Why do they become more reactive as we move down the group? So things we need to be able to do is we need to think about our observations. So when we see them reacting, what is it that we're seeing? How do we know, how can we tell the difference between them? What are they doing more or less of as we move down that group? So I'm just going to show you this very quick video clip. It's only about 3 minutes long, and in this simply we're placing the 3 different metals into 3 beakers of water, and we're just observing what happens. Does it fizz? Does it spark? We can see that one definitely does. Does it fizz? Does it spark? Does it float? Does it change colour? What's going on that's indicating to you that there is a chemical reaction taking place? Okay, so I'll hit play on the video and just have a think, just memorise some of those observations. What can you see happening?
With indulgent escapes, only the best will do. Discover our hand-picked fine star.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Zoom in real quick, let's see if we can really get in there. So this side will reflect a lot of light, the other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's been freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water. So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my two pieces of potassium in. That I've cut in half. So this is less potassium than the other two in terms of amount. You'll find that the reactivity is a little bit greater.
Okay, so I'm going to hit pause there. Okay, so in an exam question, you are often asked to note down the observations or to fill in some missing observations. So in some questions you will be given the observations maybe for lithium and potassium and asked to fill them in for sodium. So let's just think about what we saw happening there. So with lithium we saw that it floats on the water. Spell it correctly. It floats on the water. It was moving around the surface. Remember, it floats because it's less dense. It moves slowly around the surface. And it was fizzing because it was producing hydrogen gas. So we can have bubbling or fizzing slowly. And then I'll sort of set you up for a typical question, so I'll explain a question as well as filling in those observations. So for potassium you might see something about bubbles very quickly. Okay, it moves very quickly. And in here we saw some flames, didn't we? We saw sparks and we saw flames. So this is a bit of a bonus. This is what a typical exam question could look like, something like this, and you need to fill in those middle parts. So we're just going to go somewhere in between. Okay, so if we've got that lithium is bubbling slowly and potassium is bubbling very quickly, then we'll go for the sodium bubbles quickly. And what else we've got? We've got moves slowly and moves very quickly. So we'll say moves quickly. And we also saw on that we got some sparks. Now there is other observations that you could put down. So all of them eventually disappear because they react with the water producing hydrogen gas and lithium, whatever oxide, so lithium will produce lithium oxide, sodium hydroxide, etc. So eventually they react with the water, so they completely disappear. And in some cases we put universal indicator into the water, because the indicator will turn purple, showing us that they're producing an hydroxide, because they are alkali metals. And if you think to Unit 4, where we look at the reactions of metals, we know that hydroxides, lithium hydroxide, sodium hydroxide, etc., they are alkaline, and so therefore we see the solution turn purple. Okay, right, so why do they become more reactive as we move down the group? Remember, this is all about their electron structure. Okay, now this is a very common exam question, and this is what I would call a standard answer. So once you've learned the reasons as to why, we can just simply repeat it for wherever it's talking about. So in this case, I'm going to explain why sodium is more reactive than lithium, but it would be exactly the same idea as if it was asking why is potassium more reactive than sodium. Okay, so once we've kind of got that structure, it's the same reasons as why, because the same things are happening to the electron structure as we move down a level. Okay, so we are going to base it around why is sodium more reactive than lithium. So what you can see is that as we move down a level, as we move down a period, that's a row on the periodic table, we have an extra shell of electrons. So the first thing that we're going to say is that the outer electron is further from the nucleus. Because if we have, sorry, I have to concentrate on writing before I speak. If we have another shell of electrons, you can see that the distance between that positive nucleus and those negative electrons is increasing. If you imagine holding two magnets together, if you hold them close, you'll feel that pull of attraction. The further away you hold them, the less that pull becomes. So the first point is that the electron is further from the nucleus. Okay, we also have increased shielding. So the other complete shells are shielding the nucleus and the outer electron. Here we've almost got a barrier in the way. So in lithium, we're in that second shell. Sodium, we're in the third shell. Potassium, we're in the fourth. So it's moving further away, and we're increasing the shielding each time. This means, therefore, that that outer electron is easier to lose. Remember, we said the metals, they want to lose electrons. It wants to donate that electron somewhere. It wants to get rid of that outer electron. And so the further away it is, the less pull there is, so it's more easily lost. Okay, so our third point is just going to be identifying that it's easier to lose that electron. Okay, and this works for whatever examples the question is asking. Why is sodium more reactive than lithium? Because the outer electron is further from the nucleus, it has increased shielding, and therefore the outer shell electron is more easily lost. Why is potassium more reactive than sodium? Because the outer electron is further from the nucleus, we have increased shielding, and therefore the outer electron is more easily lost. Now I have seen a question that asks why is francium. We don't look at francium, it's far too reactive to have available to see these. You can find some YouTube videos of them, but just in school you wouldn't see it. But why is francium the most reactive? Because the outer electron is furthest from the nucleus, it has the most shielding, and therefore it's easier to lose the outer electron. So whatever the example, it always fits that pattern. Okay, let's jump in and have a look at a couple of exam style questions then for us. So here we've got our lower demand questions. So we have choosing the correct word, selecting the correct statement, etc. Okay, so we've got a bit of information first about the periodic table. They're often linked together because, you know, the history of the periodic table and then talking about particular groups. Yeah, it's a kind of a leading question to that subject. So it says Newland's and Mendeleev's periodic table showed the elements in order of their atomic weights. Okay, we didn't know about protons to begin with, so we couldn't put them in proton number. So following the discovery of protons and something, protons and electrons, the modern periodic table shows the elements in order of their proton number. Now when you get a question like that, please make sure that you use words from the box, don't make up your own, they're there to help you. We've got a little section then of the periodic table, and it says which one of these 6 elements has the lowest boiling point. Now this is almost testing you a little bit because we've talked about the fact that group 1 have low boiling points in comparison to transition metals. So iron is a transition metal, however we've got hydrogen labelled there. Hydrogen is a gas, therefore it will have the lowest boiling point. Okay, so we're going to go hydrogen. Okay, whether you write the word or the symbol, let's say for example you couldn't think what it was called, but you know that that one up there is a gas, so it must have a low boiling point. If you put the symbol H, that would be acceptable too. In the periodic table, rubidium is in group, well we can see it's labelled there in that bottom corner, and so it is part of the group 1 elements. Which of these elements is the most reactive? Is it lithium, sodium, potassium? We know they become more reactive as we go down the group, therefore it is potassium. And which 2 statements, be careful you check how many we're ticking, which 2 statements are correct? Okay, so we've got higher iron as a higher density than potassium. Yes, it does. We know group 1 has a low density, that's why they float on the water. Iron is softer than potassium. Iron reacts vigorously with water. Iron forms into ions that have different charges. Yes, it does. Okay, so often get asked, as I said, questions that ask you about the observations that you would see. Now for this one, it's kind of give you a little diagram to remind you of what we did, and it just asks you to describe 3 observations. Now here I'm going to say be careful that in some questions it might say when sodium is added to the water it fizzes. Give 3 other observations. So therefore you can't say fizzes because it's already been given to you in the question. So just check that it's not already giving away one in the question, because you won't gain a mark for it because it's there in the question for you. So 3 observations that can be seen when it's put into water. Okay, we're going to see fizzing. Fizzing or bubbling, however you describe it, it's producing that hydrogen gas. We're going to see fizzing and bubbling. We can say that, what are we putting in? That sodium, the sodium will disappear. And we can also say that the sodium is going to float because of its low density. Now we only have to describe, so we only have to say what's going on. Other things that you could say is that it moves around on the surface of the water. As it's reacting, we saw that they were moving around. Okay, so my tip for that question is just be careful that it doesn't already give you one in the question, so you don't repeat that because you won't gain the mark. Okay, oh, so here it is, perfect. Here's a great example of it. So here we've got another little setup. You can see there we've got the water trough with water and universal indicator in, and lithium has been placed in. It says the lithium floated on the water. 2 other observations, so we can't repeat that, we can't say that it floats. But all the other things we were talking about earlier we can, so we can still have that it bubbles or it fizzes, whatever words you choose, and that the lithium disappears. Or it moves around the water, whichever one you wish to choose. Okay, balance the symbol equation. If we've got 2 lithiums over here, we're going to need 2 lithiums on the other side. This will now give us 2 hydrogens from here and 2 from the hydrogen gas. We've got 2 oxygens, so we've got 4 hydrogens, 2 oxygens, therefore we're going to also need a big 2 in front of the H2O. Okay, describe a simple test and the result that would show that the gas was hydrogen. So this is going to be our squeaky pop. So we're going to use a lip splint, and what we're listening for is that squeaky pop. Okay. All group 1 metals have similar reaction with water. Explain why in terms of their electron structure. They all have 1 electron in the outer shell. Okay. Lithium and other group 1 metals have different properties from transition metals. They're what I was referring to as your typical metals earlier. So 2 properties that are properties of group 1. They react with the oxygen. We saw that as he cut the metals. We could see they were starting to tarnish. They react with the oxygen in the air, and they have low melting points. And the final question then, this is a sort of medium to high level question. You would find this in the back of foundation paper or in a higher paper, so it's a little bit more of a demand. So here it says that potassium is more reactive than sodium. Explain why in terms of the electron structure. Okay, so we're going to say potassium's outer electron is further from the nucleus. So just going to go through the 3 points we talked about earlier. It has more shielding or increased shielding. Okay, and then I'm going to say, so it is easier to lose the outer electron. There we go, piece of cake. Okay then guys, hope you found that session helpful, and as always, if you need any further support, please don't hesitate to reach out, and I'll see you next time for Group 7.